In this video, I'm going to derive the moment generating function for the random variable x that follows a normal distribution with mean, mu, variance, sigma squared. Now, as a review for the moment generating function, if you recall, the moment generating function is defined as m, random variable x, evaluated at t of the expectation of e to tx. Okay, so now the approach I'm going to take, I'm going to try to make this a little easier. And what I want to do is actually, I'm going to derive the moment generating function for random variable z. That's the standard normal distribution, that is. That follows a normal distribution with mean 0, deviation 1. Now, we remember the PDF, the density function of a normal distribution, standard normal distribution, that is given by 1 over square root of 2 pi e to negative z squared over 2. So we're going to call that f of z. Again, that is the probability density function of a standard normal distribution. Now, next, we're going to use this property of expectations. It's really not property, but definition of expectation of a function of a random variable. And that is given by, for the continuous case, the integral from negative infinity to infinity of the function of random variable times the density function. Okay. Now, we're going to do this for the moment generating function. Our function of variable z is e to tz. And this is going to be the integral from negative infinity to infinity of 1 over square root of 2 pi. Then we go e to tz times e to negative z squared over 2. Now, we can of course combine the exponents here. When we do in the exponent, because we're about to use the multiplication property of exponents, which allows me to combine the exponents. But let me write the exponents, because once we combine them, it's going to become this. That's going to be the exponent. So what I want to do next is I want to complete the square in z. Okay, so I'm going to factor negative 1/2. That makes it z squared negative 2tz. Now, if you remember you're completing the square method, what I need to do next is I need to add half of the coefficient on z squared. Okay, so half of negative 2t, and then we're going to square that expression. That's just going to be t squared. So I'm going to add t squared in here, and because of negative 1/2 that distributes over to t squared on the same side of equal sign, to the right side, I'm going to add 1/2 t squared. So this way I have not changed the expression. Sorry, my pen is acting up. Okay, and hold on, 1/2 t squared. Sorry about that. Okay, now next what I want to do is actually I'm going to rewrite the what's in parentheses. Okay, so I'm going to rewrite this, and this is going to become negative 1/2 z minus t quantity squared plus the half t squared. Okay, and that's what we're going to take to our integrand when we do our integration. Therefore, the expected value of e to tz is going to be the integral from negative infinity to infinity, 1 over square root of 2 pi. And here's where I'm going to rewrite. I'm going to put this in the exponent when I combine using multiplication rule of exponents. So for doing that, I'm going to get negative 1/2 z minus t quantity squared plus 1/2 t squared. and then there's dz. Of course, I realize that most textbooks and most everyone, not just textbooks, 1 over square root of 2 pi is a constant, so you can bring it outside the integrand, outside the integral. But I'm going to keep it there for a reason. Okay, so instead what I'm going to do is this. I'm going to write this as negative infinity to infinity, and then I'm going to go ahead and do this part. That's going to be e to t squared over 2 times, and now I'm going to write all the rest of that stuff. 1 over square root of 2 pi, and then e to negative 1/2 z minus t quantity squared dz. Okay. Now, once I bring that e to t squared over to outside of the integral, then the integrand, all that remains in the integrand is this expression, correct? And the integral from negative to infinity, from negative infinity to infinity of that is just the area under the normal distribution. So all of this expression is equal to 1 because that is just the area under the normal distribution whose mean is t, deviation is 1. Okay, and I'm thinking z minus mu over sigma squared. Remember that part of the exponent for the general normal distribution. So instead of mu now, we have t, and of course sigma is 1, right? Now let me tidy up all of this, and we'll continue on. Okay, so indeed what we've done is we derived the moment generating function for a standard normal distribution. Now what I want to do next is actually I'm going to derive the moment generating function using this for the general random variable x. So here we go. To get the moment generating function for random variable x that follows a normal distribution with mean, mu, variance, sigma squared. So what am I going to do? I'm going to let, if you remember the standardization formula, your standardization formula was z equal x minus mu over sigma. And in this expression, if you solve for x, multiply both sides by sigma, add mu to both sides, you're going to get z sigma plus mu. Okay, so I'm going to do expected value of now e to tx. Notice my random variable now is the general normal distribution. X, whose distribution is the general normal distribution. So here the expectation is going to be e to t. I'm just going to put z sigma plus mu here, right? Remember that's what x is from this step right here. Okay, what are we going to do next? Next, I'm going to actually break this inside the bracket. I'm going to write it as e to mu t. That's mu and then t. In other words, I'm distributing t and breaking the exponent into 2 parts, a product of e to, and then it's going to be sigma z times t, right? That's what that's going to be. Now, one of the properties of expectation is that if the expected value of a constant multiple of a random variable, you can bring the constant outside times the expected value of the random variable. So with respect to our random variable, remember it's z. Our random variable is z. So mu t, that's just a constant, and e to that is a constant again. So I can actually bring e to mu t outside times the expected value of e to sigma, and I'm going to put, let me use a different color here, because what I want to do is I'm going to now combine sigma and t, and then times that by z. In other words, I just rearranged those factors. That's all I did. Okay. Now, the reason I did that is because we just, didn't we just do expected value of e to tz, and that turned out to be t squared over 2. Well, instead of t now, we have sigma t, which is again a function. It's a function of, think of it, variable t. So what that means for me is that I can write this as e to mu t, and then the expected value e to t sigma z is going to be simply e to t squared sigma squared divided by 2 using this. Okay, and we are almost done. Indeed, the next step we will be done. So the moment generating function, now we can use the multiplication property of exponents and combine the two exponents. We get mu t plus sigma squared t squared divided by 2, and that is what we wanted to do. So that is the MGF, the moment generating function for random variable x that follows normal, mean mu, variance sigma squared. And that will conclude our video.